Welcome, dear friends, to this lecture series on power plant economics. The objective of lecture today is to explain you the concept of a very interesting concept of economic scheduling, and this we would be explaining with the help of one concrete example. By economic scheduling, we would be highlighting the economics behind the scheduling of power plants, and the example being taken is a coal-based, gas-based power plant system. Uh, Economic scheduling, I need to define it first, and if you can just think of this power system wherein there are some two units. One is a coal-based power plant and of a particular capacity, and other is a gas turbine-based power plant of some capacity. Okay, and let us say this is a thought exercise. Let us say that the overall capacity is to be satisfied is 100 megawatts. Okay, and suppose it is known that a coal-based power plant is more efficient. Okay, by more efficiency we mean that the coal-based power plant consumes less coal per unit of electricity generated. Okay, and the running cost is also less. The heat rate is less. Okay, that is let us say is a particular coal-based power plant in our thought exercise, and there is another gas turbine-based power plant which is relatively speaking less efficient, has a higher heat rate, and it consumes more fuel per kWh. Obviously, it has more running cost, more variable cost. Let us say that we have a demand of 100 megawatts. Okay, and a capacity of unit A is 100 megawatt, a capacity of unit B is 100 megawatt. Now somebody might say that, okay, look at this, a coal-based power plant is most efficient, so why not just keep gas turbine-based power plant closed, okay, and simply schedule the power system with only coal-based power plant. Okay, so this could be one understanding, right? And this appears to be a very logical kind of understanding, because as it is given in this thought exercise that the coal-based power plant is more efficient with a less heat rate, it consumes less fuel. Okay, but as you would realize as we proceed with this discussion on economic scheduling, that is not always the case. Okay, so economic scheduling means to decide upon a criteria. Okay, decide upon a criteria, and that criteria is a minimum variable cost. How much electrical demand would be met by unit A in this case, and how much would be met by unit B? And what is the criteria? The criteria is that the overall cost, I mean the variable cost, the fuel cost is minimum. Okay. In order to understand this, we need to look at some concepts, very elementary concepts. So one concept which is displayed here on the board is the graph which you see, which is the heat rate versus the power output. Okay. Now heat rate, let me define heat rate first. Efficiency, you all know, efficiency is of a thermal power plant is the output. Efficiency is the thermal output or the electrical output of a thermal power plant is the electrical output upon the energy which is released by the combustion of the fuel. Okay, that is the efficiency, right? So generally speaking, it would be the load which is made by the power plant, which will come in the numerator, and in the denominator it would come the fuel consumed and its calorific value. The multiplication of the product of the fuel consumed and its calorific value would come in the denominator. That becomes the thermal efficiency of a power plant. Heat rate is the reciprocal of that. Heat rate is a reciprocal of efficiency. So obviously a more efficient power plant would be having least heat rate, right? A less efficient power plant would have more heat rate. So a lower value of heat rate is desirable. Okay, so if you look at this way, then if you look at the curve over here, you will find that the heat rate, typical heat rate versus load curve is of this form, and you see that when the load is initially lower, the heat rate is higher, which is not desirable. And as you go on increasing the load on the power system, the output power as it increases, the efficiency would improve, the heat rate would reduce. Okay, and you would find that somewhere near the rated capacity of a power plant, this value is typically much lower. Okay. And then again, you would have a slightly increasing heat rate curve. So this is a typical heat rate curve. Okay, heat rate versus the load curve, which we need to understand. And anybody who has studied power plants, they know that this is a typical profile. Okay. The other important curve which one needs to look into before we understand economic scheduling is this curve, which is the input versus output curve. Okay. Now on the input side, which you see on the y-axis, it is the input power, okay, which is nothing but the rate at which the energy is released into the power plant. Okay, that is the fuel consumed into the rate of fuel consumed into its calorific value. That is the input power to any power plant, right? When you are talking about fossil fuel based power plant, and the output power is in the is represented on the x-axis, and that would correspond to the load which that power plant is handling. Okay, so look at this way, you'll find that obviously it would have a linear kind of relationship, and as the output power being met, okay, or being generated is more, as it increases, obviously the input power would also increase, right? And this curve, you see that there is a change in the slope, and you can think of that why the slope is not the same. You would understand that is because the efficiency is different, okay, at different percentage loading. Okay, so this typical input versus output curve would help us calculate what is known as the incremental fuel cost. Okay, so suppose instead of plotting the input power, if I calculate and the corresponding fuel cost for that input power, okay, and put it on the y-axis, and the corresponding load on the x-axis, or the output power on the x-axis, then what you'll have is a similar curve wherein it is a fuel cost versus the load curve. And if you take a slope of that, that would be called as an incremental fuel cost, right? So that is the incremental fuel cost. Now incremental heat rate tells us, and this incremental heat rate is a very important concept. Incremental heat rate tells us how costly it is to produce next unit of electricity, right? It is because what is more important is the electricity, every unit of electricity produced is more and more economical. So if we know the incremental heat rate, one can estimate what is the incremental fuel cost, and that incremental fuel cost versus the output, versus the power output, is the curve which you would see, which is a linear approximation is shown here, and also the actual incremental cost curve is also seen. Okay, so please note that the incremental heat rate tells us how costly it is to produce the next unit. By unit we mean kWh, kilowatt hour of electricity, right? And this is a very important concept when we are talking about economic scheduling, right? We would always aim for a lower cost, okay, for producing the next kWh by that power plant. So what now is economic scheduling? As we had discussed in abstract, economic scheduling is about deciding the scheduling of the power plants based on the overall running cost, okay, which has to be kept as a minimum. Okay, it does not mean that only one unit has to be operated at full capacity and then the second unit should be brought in action. Okay, and how is that to be understood? So we'll be taking an example now, that let us say that there are two units, one is unit A and other is unit B. Unit A, let us say, has an input A and unit B has an input B. So we would be using the notations I for denoting the fuel input, and we would be using the notation L to denote the power output or the load which is being handled by that particular unit. Okay, so the condition for economic scheduling would then be stated as the input cost, that is the input A plus input B, is to be minimum all the while the plant is in operation. Okay, or in other words, the incremental heat rate has to be kept as minimum. So mathematically speaking, it could be represented as a derivative of d of IA plus IB, okay, LA, DLA is equal to 0, right? So DIA by DLA, which is the differentiation, plus DIB plus DLA, which is again a differentiation, that is equal to 0. Meaning is we are now putting a condition. We are now putting a condition of scheduling the unit A. Okay, we are now talking about scheduling of unit A such that the cost is minimum. Okay, the input is minimum. Equation 1, which is written over here, is just a rephrasing of, or just rewriting of the expression DIA by DLA plus DIB by DLA. Okay, so what I have written is DIB by DLB is equal to negative of DIA by DLA, right? And now that's some mathematical jugglery we would be doing. We'll be just rearranging certain terms so that I will be getting the expression which I have in mind. Okay, the expression which I have in mind is I am now aiming to derive an expression for economic load scheduling. Okay, so as you see over here, I have rewritten DIB by DLB as DIB by DLA into DLB by DLA. Okay, this is just rewriting of the expression. Okay, and you know that DLB by DLA is equal to -1. That is because you know that L, the total overall load on the power system, let us say that is L or LC, that is equal to LA plus LB. Okay, and because that total load would not change with respect to LA, so DL by DLA has to be 0. So using all this mathematical thing, what you would come across is DLB by DLA comes to be equal to minus DLB by DLB. Okay, so this here it has to be DIB by DLB. So equating equations 1 and 2, if you equate the equations 1 and 2, you get a very important, just forget this derivation. What is important for us is this expression, that is the expression is DLA by DIA by DLA. There is a small mistake while doing this slide. DIA by DLA is equal to DIB by GLB. Okay, now that condition that DIA by DLA is equal to DIB by DLB is the condition for economic scheduling or economic load scheduling in case of power plants. Now what does that mean? It means that the combined input of unit A and that of unit B is minimum only when the incremental heat rate of unit A is equal to incremental heat rate of unit B. This has to be kept in mind. What is the condition for economic scheduling? The condition for economic scheduling is that the incremental heat rate of unit A is equal to the incremental heat rate of unit B. Remember that it is not the same as equal loading of unit A and unit B. And it is also not the same as operating the most efficient unit first. Okay, this has to be kept in mind. To help you understand this better, let us take an example, a concrete example, wherein there are two units. One is unit A of capacity 200 megawatt. There is another unit B of capacity 200 megawatt. And you are supposed to determine the economic scheduling for unit A and unit B. What is given is the incremental heat rate for unit A and incremental heat rate for unit B. So DIA by DLA is given to be 0.065 LA plus 25 and DIB by DLB is given to be 0.08 LB plus 20. Okay, these are the incremental heat rates for unit A and unit B. And what you are required to do is you are required to schedule this system. That is, you need to tell the manager of that power plant that which unit has to be operated when. Okay, so a layman would say that okay, there is 200 megawatt, so let us operate unit A at 100 megawatt and operate unit B at 100 megawatts. So 100 plus 100 becomes 200. So, but that would be scheduling, but that won't be economic scheduling. Somebody would say that, okay, you operate 200 megawatt unit A and keep the unit B shut down. Okay, because your load to be met is only 200 megawatt. Okay, that is also scheduling, but that is not economic scheduling. Similarly, one would argue that you operate only unit B, keep unit A as idle. Okay, so this all the three options, they are all scheduling options, but they are not economic scheduling option. Now, then if you want to schedule it economically, meaning that if you want to ensure that this power system is operating at the minimum fuel cost, then the condition is the incremental heat rate of unit A has to be equal to incremental heat rate of unit B. In other words, 0.065 LA plus 25 has to be equal to 0.08 LB plus 20. Okay, this is one equation. You will say, you will call it as equation 1. And the second thing which we know is it is given that the total demand is 200 megawatts. So LA plus LB has to be 200. So these are two simultaneous equations with two unknowns, and we solve them. You get a very interesting thing, that is we get LA is equal to 75 megawatt and LB is equal to 125 megawatt. In other words, what it means is that if we operate this given power system to meet the demand of 200 megawatts such that the unit A handles 75 megawatt and unit B handles 125 megawatt, in that case, the total fuel cost would be minimum. Okay, it would be the economic scheduling. I hope this is very clear to you. The outcome of this lecture is that you have understood what is economic scheduling, and we have taken a very simple example to stress this point that economic scheduling, though the term appears to be a bit threatening, is indeed a very interesting and very useful concept for in the power plant economics course. Thank you very much.